Assalamualaikum and good day. In this video, we would like to present our assignment for power system design and operation, which titled Capacitance of a two-wire line. I am Muhammad Haziq bin Jamari, and my group members are Alexander Anderson Ana Anthony and Nik Marisa binti Nik Mazlan. So first we go to the introduction. Capacitance is the ability of a component or circuit to collect and store energy in the form of an electrical charge. It is with the symbol of C and farad F as the units. The capacitance in a transmission line is caused by the difference in potential between the conductors. Parallel conductor capacitance depends on the conductor size and spacing. In addition, the transmission line produces two kinds of fields, which are magnetic and electric fields. Next, we go to the effect of capacitance. In transmission line, capacitance creates shunt admittance. For transmission line shorter than 50 miles, which is 80 kilometers in length, capacitance is often ignored. So the effect of capacitance is the constant supply of reactive power results in a higher voltage drop along the line, a decrease in the line's efficiency and power factor, and a disturbance in the system's stability that the line is a part of. So there are two methods for derivation, which the first method is derivation using Gauss law. For derivation using Gauss law, assume there are two wires moving in z direction. General point on z plane with the coordinate x, y, 0 is called point P. Orange line is a positive line charge, while blue line is the negative line charge. To calculate the potential for a line charge, V is equals to rho L over 2 pi epsilon ln Rd over R, where Rd is equals to position in radial direction where V equals to 0, while R is radial direction where potential is V. In this derivation, we let R10 is equals to radial distance for positive line charge, while R20 is equals to radial distance for negative line charge. And in this derivation, we also assume R10 is equals to R20. Next, we substitute our R inside the equation for V, which the equation will be V equals to rho L over 2 pi epsilon ln R2 over R1. From the figure, we can see that R1 is equals to square root of bracket of x minus a power of square plus y square, and R2 is equals to square root of bracket of x plus a power of square plus y square. And then we substitute R1 and R2 inside V, and also we assume K1 is equals to bracket of x plus a power of square plus y square over bracket of x minus a power of square plus y square. And then at the end, we will get K1 is equals to E exponents power of 4 pi epsilon V over rho L. Then, from previous, we know that K1 is equals to bracket of x plus a power of square plus y square over bracket of x minus a power of square plus y square. By doing cross multiplication, we will get bracket of x minus a bracket of K1 plus 1 over bracket K1 minus 1 power of square plus y square, and equals to bracket of 2a square root of K1 over bracket of K1 minus 1 and power of square. Then we know the radius of the circle given by 20 square root of K1 over K1 minus 1 is equals to B, and the center, which the coordinate is h0, h is equals to a in bracket K1 plus 1 over K1 minus 1. And then we solve for a is equals to square root of h squared minus b squared. Square root of K1 is equals to h plus square root of h squared minus b squared over b, and square root of K1 is equals to exponent power of 2 pi epsilon V naught over rho L, and also for rho L is equals to 4 pi epsilon V naught over ln K1. And by referring to the equation of arc cos x is equals to ln x plus minus square root of x squared minus 1, where the x is the range of 1 until infinity, in form of capacitance C. C is equals to 2 pi epsilon L over ln h plus in square root of h squared minus b squared over b, Thus, the final expression will be C is equals to 2 pi epsilon L over inverse cos H over B. So that's all for the derivation using Gauss law.
Method 2, Part 1. Capacitance between the conductor, which is single phase with two wire line. Consider a two-wire single phase line of conductor A and B, whose representative radii are RA and RB, separate by a distance D. Between the conductor, the voltage VAB is generated by the charge on each. VAB, the charge on conductor A, as you can see, the formula is VAB equal A is equal to integration of D to RA EA dx is equal to Q over 2 pi E0 ln D over RA, while VAB, the charge on the conductor B, which is VA minus B, is equal to the integrations of radius B and diameter EB dx is equal to negative Q over 2 pi E0 ln RB over D. Thus, the total voltage VAB is equal to VAB of A and plus VAB of conductor B is equal to Q over 2 pi E0 ln D square over RA RB. This is based on the law of superposition, which is owing to the charge of both conductor, the potential difference between the conductor A and B is equal to the total voltage of the B due to the each charge alone. If the conductor have the same radius, which is RA is equal to RB is equal to R, VAB is equal to Q over 2 pi E0 is equal to time ln D over R. Hence, the capacitance between conductor A and B for a 1 meter length line is equal to CAB is equal to pi E0 over ln D over R in the unit of F over M. Method 2, Part 2, Capacitance between the conductor and neutral point or ground. Based on the preceding discussion, we know that the neutral point, which is corresponding to the zero potential line, is midway between the two lines. Therefore, assuming that the VAB is the precise spot, the voltage reference between the positive and negative points to VAB is the half of the voltage, since the voltage at the neutral or ground point is zero. Thus, the capacitance due to any one of the conductor is equal to CAG or CBG is equal to lambda over V over 2 is equal to 2 lambda over V. From the above discussion, we have determined that the capacitance between the two line conductor is CAB is equal to pi epsilon naught over ln D over R in the formula of F over M is equal to lambda over V. After substituting the formula, the capacitance per meter length for each conductor to the neutral point or ground is therefore is equal to CAG is equal to CBG is equal to 2 pi epsilon naught over ln over D over R. This is very important for the line and modeling analysis. The capacitive reactant to the neutral or ground is obtained through the formula Xc is equal to 1 over 2 pi F CEG. After substitute the value of the capacitance per meter length, Sc is equal to 1 over 2 pi F 2 pi epsilon naught over ln D over R is equal to 1 over 4 pi square epsilon naught ln D over R. Consequently, the final formula for calculating capacitance reactance to the neutral or ground is Xc is equal to 2.862 over F times 10 to the power of 9 ln D over R.
So we have come to the part where we'll be explaining about two examples, which this one is the first example 1, where it goes with a single phase with 50 Hz transmission line that has conductors with diameter of 2.4 cm and distance between centers of conductors of 305 cm. Hence the question asks to calculate first one is the line to neutral susceptance for the line in mole per kilometer, and the second Roman asks for capacitive reactance of the line in ohm considering the line length of 80.5 km. here are the example 1 solution, which first we need to find the radius of conductor, and since the previous diameter is in centimeters, so we need to convert it into meter. So with 2.4 will be divided by 2 times hundreds, we obtain the radius to be 0.012 meter. To answer the first question, that is to find the capacitive reactance, silap lah. That is to find the susceptance, we first need, by using the formula, and we have known that the value of the distance between two conductors is to be 305 centimeter. Hence we converted it into meter, giving out to 3.05 divided by the radius. And the answer is to be 3.16 times 10 to the power of 8 ohm meter to neutral. So we need to, as the question asks for it to be in kilometer, so we'll be divided by 1000, giving out 3.16 times 10 to the power of 5 ohm kilometer to neutrals. Hence right away the susceptance can be calculated by using the formula 1 divided by reactive capacitance, which is 1 divided by the XC, is equal to 3.16 times 10 to the power of negative 6 mole per kilometer to neutral. As for the second Roman, on finding the capacitive reactance of the line for 80.5 kilometer, the answer could be directly just XC that has been obtained in Roman 1 divided by 80.5, giving out the answer to be 3925.5 ohm. As for example 2, it is given a single phase with 50 Hz transmission line that consists of two conductors which are separated by 5 meters from each other. The radius of each conductor is 2 cm. Hence, it asks to obtain the susceptance of the line to neutral in mole if the length of the line is 40 km. So the solution is, first we list down all the given informations, that is the radius must first convert it to meter. From 2 cm it will be 0.02 meter, and the distance will be 5 meter. So all this information will be inserted into the formula, and after derivations of the XC, the distance and radius could be directly inserted, resulting to 3.1605 times 10 to the power of 5 ohm kilometer to neutral. And again, as previously explained in example 1, in obtaining the susceptance, we just right away use the formula 1 divided by XC, giving out 3.1641 times 10 to the power of negative 6 mole per kilometer. And since the question asks for the length of the line that is 40 km, so we multiply with 40 km, and it's equal to 0.1267 times 10 to the power of negative 3 mole, which is approximately 0.13 times 10 to the power of negative 3 mole. That's all from me. Thank you.
The capacitance of two wire line, or in overall, as the general formula of capacitance is C, which is the capacitance is over the charge of the conductor, which is Q over voltage. The capacitance is the ability of the component or circuit to collect or store energy in form of electric charge with the symbol C and unit F. Due to the potential and capacitance is happened due to the potential difference between the conductors. And the capacitance between two parallel conductors is depend on the size of the conductor and spacing between the conductor. When the effect of the capacitance is causing the high voltage to drop, and power factor of the line to decrease, and it could form a shunt admittance in transmission line, and capacitance is neglected for transmission line that are less than 80 km. As shown, we have derivation method 1 and method 2, and method 1 is derivation using the Cartesian axis, while method 2 is capacitance between the conductors in single phase with two wire line using electric field. So that's all for today, and thank you.